This brings us to our last good idea, which is to distinguish the public keys that we use to get started from the session keys that we use for the communication in the session. So Alice, knowing Bob's public key, will contact Bob and say, "I'm Alice, are you Bob?" Bob proves that he is Bob by signing something, but now not just an R, but some new private key. And then Alice can decrypt that message using Bob's public information to get the private key. And then she could encrypt all requests going forward using that private key. And Bob can send back answers, again encrypting using that private key. So we can use something like AES with this kind of key. This is a short-lived key used just for this interaction with Alice and Bob. The next time Alice contacts Bob's service, then they will generate a different key to use with that future session. But there are still a couple of problems here. One is that Bob is sharing this key he synthesized, still using, he's signing that key, but anyone who knows Bob's public key could decrypt that particular key. And also, still, if Bob's private key is ever compromised, then if a key is sent, even in an encrypted message, if we solve the problem that everyone has Bob's public key, then still that key is in the message somewhere, and the conversation can be exposed in the future. To solve both of these problems, we can use Diffie-Hellman to avoid ever sending the key directly in a message, and only sending messages that are encrypted with that key. That is, when Alice contacts Bob in the first place, she says, "I'm Alice, and here is my public key for this session." And Bob can use his private key, separate from his RSA private key, but his session private key, to generate the brown paint, which is a shared key, which Alice can also generate as soon as she gets Bob's orange color sent back. So when Bob sends the orange, again, everyone could decrypt this message using Bob's public key to see the orange, but no one can arrive at the same brown paint shared secret that Alice and Bob have. So these keys are never sent over the network. Only messages encrypted with the keys are sent over the network. So Alice and Bob now have a shared key that's just for the session that no one else has, that isn't exposed in the message, and furthermore, it isn't exposed in the future. If Bob's private RSA key is ever compromised, old sessions between Alice and Bob, once they're terminated, the shared known secret goes away, and so those old messages cannot be decrypted either, even though the starting RSA private key got compromised. This property of the protocol is called perfect forward secrecy, meaning that the session is secret when it was happening, and also in the future it will stay secret even if the key used to kickstart that conversation gets compromised.